Okay, let's start the session. This session is the Wednesday morning session for particle physics. So this session will basically we hear from CMS and Atlas and model experiment for especially for dark matter search and Bsm result. The first, so the talk is given in total 20 minutes, and so first talk will be search for dark matter CMS given by Andre Albert. So can you start?
Yes. Thanks for the introduction. Okay, so I'll be talking about dark matter searches in CMS. And I think it's pretty clear at this point that dark matter is important for us to understand as a field in general. And for me as a particle physicist, really the question is it a WIMP? And if so, can we find it in the lab? And if we want to find new particles in the lab today, usually we do this at the LHC. And the way to do this is you observe proton-proton collisions with a multi-purpose detector such as CMS, which allows you to cover the full event and really get all of the collisions that you can in a broad range of final states. With these devices together, over the last 5 years, we've collected data that amounts to an integrated luminosity of about 140 inverse femtobarns, a center of mass energy of 13 TeV. So that means we have a data set in hand that is unprecedented, not just in energy, but also just in sheer size. And the combination of these two makes this a very potent tool for discovery that we now have at hand, and that we have analyses using the full data set at this point. I'm going to focus in this talk on really analyses that use the full data set because I think those are the most exciting ones at this point in time. If we want to discover a dark matter particle at the LHC, unfortunately, we can't find it directly, so we don't have the type of detector technology that was discussed in the plenary talk just now, where we find dark matter interactions directly. And most importantly, we don't have the type of particle flux that would allow you to do this. So we have to rely on indirect ways of finding it. The way to do that is that we look for missing transverse momentum. The idea here is that if we have a collision where visible and invisible particles are produced, the visible particles will be kind of lopsided, and their imbalance tells us something about the momentum carried away by the undetected particles. So that's shown in the cartoon here. And of course, that implies that these additional particles have to be produced. So we need to produce something in addition to the dark matter in order to find these events. And the interesting thing now is that by looking at different types of these particles that I will call tags, we can zoom in on different types of interactions between dark matter and the standard model matter. And we're not at this point yet, but if there were ever a signal here, this type of complementarity between different channels can also tell us more about how exactly the interaction would look like. So this is also an interesting post-discovery tool, but okay, we're not there yet. On the right-hand side of the slide, I have a few different interactions of how this could look like. In general, these are kind of examples that guide our searches, but none of the searches are really exclusive to one of these. And there's a lot of general search strategies. So here, roughly in order of complexity, we have something like a very simple model of dark matter interactions. So we just have a new mediator that couples to quarks and dark matter. In that case, the tag is just radiation. For example, here a gluon, which just occurs generically. We can look at a type of Higgs Portal model where we don't have a new mediator, but the quote unquote standard model Higgs at 125 GeV also couples to dark matter. And there the tag particles are dominated by how the Higgs is produced in the standard model. So for example, VH production here. And then you can also go to more complicated models where you have multiple additional new mediators that couple to each other, and you have couplings to bosons and so on. And really there's a large complexity that you can explore. I'm going to start by talking about a first result that just came out last week, so it's very fresh, a monojet mono-V search. If you're not familiar with this jargon, what this really just means is that we do a combined search in hadronic final state. So we look at jets plus high transverse momentum imbalance. And here we do a combined search that really aims to target different things at the same time. It aims to target the case that we have on the left with narrow jets from QCD radiation that we're going to call monojet. And on the right-hand side, something like a vector boson decaying to a fat jet made out of 2 quarks, and that we're going to call mono-V. The search is based on a tagger that allows you to generically identify for a fat jet what its decay topology is. And you can see here the output score of this tagger. It does a really fantastic job of differentiating between QCD jets and the vector boson jets. And then if the tagging score is low, or maybe we have only narrow jets, no fat jet, it goes into the monojet category. And if the score is high enough, we sort it into the mono-V category and split that further into low purity and high purity in order to optimize the signal over background ratio. In addition to those, you then have to require also high missing ET, so at least 250 GeV in order to be able to trigger this in hadronic final states and then do some cleanup selection and so on. So, but that is kind of a just decoration. I'm going to say the main principles is the categorization and high missing ET. Then, after we've done the selection, one thing to understand about these dark matter searches is that typically they're not background free. So specifically here we see the signal region of the monojet category, which you can see is dominated by Z's and W's. That's just where neutrinos come from. So that's how we get high missing ET. And that's really the main source of background that we can't reject by selecting. So we have to estimate it. And we do this in a method with a maximum likelihood fit with control regions. And the idea is that we pick control samples and data that have processes that are very similar to what we want to constrain. And then we use transfer factors to connect the control regions to the signal regions. Those are the blue arrows here. And the idea is that then we can let the background estimate per bin in the signal region float freely and thus get the kinematic shape of the distributions from the data. This is a fantastic method because loads of the theory uncertainties, for example, cancel. Everything that's really common in uncertainty between control and signal region cancels out. That is a great way of reducing our uncertainties and using the statistics that we have in this big data sample to make this happen. So then we end up with 5 control regions per signal region, and we have the different signal regions for the different categories. And in the end, we just combine everything in one likelihood and fit everything together in order to extract the background and possibly the signal. We do not see a signal here, as you can convince yourself on the left-hand side from the background only fit that's shown here. And so we arrive at constraints for models where we know that, that they can be realized in this way. And here I show you 3 examples, but I want to stress that these are examples in the sense that the sensitivity is not really specific to any of them, but rather generic to any jets plus missing ET type topology. So yeah, I really want to stress this general aspect of this type of search. And the examples that I show you here from left to right range from very simple, something like a heavy Z boson on the left or a heavy Higgs in the middle. In this case, it's a pseudoscalar that we look at, so it's spin 0. We also look at scalars that would really be more Higgs-like, but we assume Yukawa suppression of the quark couplings, which is why I would call it Higgs-like. And then on the right-hand side, something that's more inspired by a leptoquark, where we have a mediator that couples to a quark and a dark matter particle. Generically, the constraints here are put in the plane of the mediator mass and the dark matter mass on the x and y axes, and all the couplings are set to some benchmark values. And generically, you can see that we probe masses of about 2 TeV for spin 1, here 500 GeV for the pseudoscalar. This is reduced because of the Yukawa suppression. And then on the right-hand side, we're up to 1.5 again. So really the mediator mass range that we can cover is from a few hundred GeVs if we have some special suppression up to maybe 2 TeV if we don't. And the dark matter mass sensitivity typically is about half the mediator mass sensitivity, simply because we have this kinematic cutoff. So if you go above this diagonal here in this plot, the decay of the mediator to dark matter is suppressed and can't really happen, and that kills the sensitivity. One thing that I want to stress here is that because this is so general, we also spend a lot of time trying to think about reinterpretations And we publish reinterpretation material for this type of search. If you're interested in that, the HAB data entry is at the top here, or feel free to ask after and we can talk about this. But we really want to foster interpretations in different models also by theorists and other recasters. I did not tell you anything yet about why we should care about the MonoV search. So the part that I just showed you is heavily dominated by monojet. I'm going to come back to this, but I first want to stick to these models for a second, specifically the spin-1 case, where I think an interesting way to look at this also is to look at searches for the mediator directly, because what I just talked about, the search strategy applies to the diagram in the top left. But of course, you might also wonder, is there maybe scattering of quarks back into quarks, which is kind of unavoidable if you have the diagram in the top left, or maybe even scattering into leptons. You don't need to assume lepton couplings, but there's also no one preventing you from doing it. So it's kind of an extra dimension that you can explore. And we do this in a systematic way by looking at resonance searches. So for example, in the bottom left, we have a dijet search. Bottom right, we have dilepton searches. They're very similar in the strategy in the sense that we have a smoothly falling background and we need to find a little bump on top of the background. And they're complementary in the sense that dijets have fantastic cross-section. So even without a signal, you see something like 8 TeV mass events, which I think is really a number that you have to think about a little bit to appreciate it. And the dileptons really profit instead from having fantastic resolution. So if you look at specifically the electron channel here, the mass resolution here, even at high masses, is really good. The constraints from this type of search, instead now of a triangle, they're kind of a vertical band instead. We see this here on the left for the dileptons, where the lepton coupling is pretty free because we don't need to assume it for production. And if it's small, you can see that the constraint is mostly above the diagonal, where there's no branching fraction of the mediator into dark matter that would take away from this branching fraction into leptons. And if you turn it up a little bit to even medium values like 0.1, you already get significant constraints also below the diagonal. For dijets on the right-hand side, in the benchmark coupling case that I showed you before, the quark coupling is set to 0.25. And here also we get these yellow areas here. So also significant constraints also below the diagonal into the TeV range. So these analyses are really powerful in constraining the high mass mediators. Of course, when you see the plot on the right, where the monojet result that I showed you is the red curve here, you might wonder, why do we even do monojet at all? It seems useless if the dijets are so powerful. And that's true in the benchmark coupling case. But to really understand this, we have to look at the coupling dimension in a little bit more detail. And on the left, you see the coupling limit plot for the dijets, where we have many different lines simply because we need different search strategies for different points in this mass range here because the trigger requirements change. There you can see that we probe couplings down to something like 0.06. And it's important to understand that this coupling here, GQ prime, assumes that there's no branching to dark matter at all. If we look at monojet, on the other hand, the coupling assumes a branching fraction into dark matter, of course. And here we could probe values down to something like 0.02 here for this quark coupling. And if we wanted to compare apples to apples, we would have to take the left plot and make it worse by about a factor of 2. So you can see that there's really quite a significant gap in the coupling sensitivity here. And monojet really dominates at low couplings. And it dominates at low masses. But then the dijets take over higher masses, higher couplings. So the two types of searches are really completely complementary in that sense. And it's important that we do them both and not just one of them. With that, I'm going to come back to the thing that I mentioned at the start, which are interactions with bosons. Since we've now really covered the spin-1 case to great detail. And here I want to show you a mono-Z search. This is in terms of topology similar to mono-V, but now the Z decays leptonically. And the great strength of this type of search is that we don't have to rely on missing ET triggers, so we can explore much lower ranges of missing ET. So you have the Z boson here that decays leptonically, that allows low threshold triggers, that allows you to easily select this final state. It's really fantastic to work with at the LHC because it's such a clear signature. And then you can use this to probe this type of resonant decay where you have a heavy new scalar Higgs that decays into a Z and a pseudoscalar mediator A, which then goes to the dark matter particles. In the middle here, you can see the signal regions. The signal extraction here is done on the transverse mass, which allows you to have a little bit of a peak here in the signal. That's the green line. And you can use that to differentiate a little bit from the resonant and non-resonant background, excuse me. And apart from the topology being different, the strategy here for background estimation is very similar to the hadronic search that I talked about before. Again, control regions, transfer factors, and so on. And the fit method is really very similar. When you then look at the constraints here that come out of this, you can see that in the plane of the pseudoscalar mass and the heavy scalar mass, you probe masses up to something like a few hundred GeV in the pseudoscalar, something like 1.2 TeV in the heavy scalar. So this topology is really very sensitive to this type of boson interaction model and allows you to probe mass ranges that are similar to what you get from the hadronic search, but now in a specific type of model that really is kind of tailored to this type of topology. And yeah, so this really highlights, I think, the complementarity, because if you were using this mono-Z search to search for the same model as you would do in monojet, you would see that mono-Z has very much reduced sensitivity, and you would think that it's useless. But by exploring different type of interactions, we actually see that it is very useful indeed. And then the final interaction here that I mentioned at the start is the Higgs portal. And here we're kind of closing the loop a little bit. In the Higgs portal interpretations, the limits are typically defined as branching fractions for Higgs to invisible particles. We get constraints here from the ZLL search that I just mentioned in the 20% range. But also we see now that we get constraints from the hadronic search, where you can see that the mono-V actually dominates. So monojet also has contributions from gluon fusion, so that's good. But mono-V with this VH production is actually even still a little bit better. And that's really the main aim of why we have this combined search in the two categories. And when we combine them, we get an even better limit, which then in the end also ends up in the upper 20% bracket. In the end though, these are not the most sensitive results yet, because here everything is about combining. And I'm showing you here the combination on partial run-through data. We don't have the full result yet. And we can see that the result is dominated by the VBF analysis, which I don't have here yet, unfortunately. But as soon as that one is also out with the full run-through data, we're going to redo the whole combination and get better. But for now, the best result that we have here from the partial combination is 19%. So just under the 20% mark. The sensitivity, as you can see, was already a little bit better than the expected. And we expect to really break the 10% barrier here as we go to the full run-through combination. I think we're on track here based on the results we're seeing for the channels that are already out. There are, of course, millions of other searches that I unfortunately couldn't talk about, sometimes because they have only partial data sets, sometimes because the talk time is just too short. But I invite everyone to have a look at these and kind of convince yourselves that we're trying to cover this type of search from really all the angles that we can, from additional tag particles to completely different views of the dark sector by looking, for example, for dark photons, which are in the middle, or going into SUSY-like topologies, which is shown on the right. We try to do all of it, and there are various results here really that are very interesting, I think. With that, I'm going to come to my summary. I hope I could convince you that dark matter at CMS is really core of the physics program. So it's not a niche thing we do, it's really at the core. And we try to do it in many topologies, as I mentioned, and try to think about different interactions so that we really cover all the ground that we can. With the full run-through data set, we have constraints that are typically in the TeV range for our benchmark coupling scenarios. I don't want to quote a single number here because it all depends on the couplings that you choose and so on. But typically that's the range. We live in hundreds of GeV to few TeV. And we're going to keep improving on this. And we still have results that are scheduled to come out. Specifically, I mentioned the Higgs portal there to come. But we also have more of the standard, quote unquote, dark matter searches that are still to be updated with full run-through. And I invite you to check back in periodically to see how that goes. Thank you.
Okay, thanks for the very interesting talk. So we can have just one question. Yeah, otherwise we can have the second talk because we are a bit behind the schedule. So the second talk will be searches for Higgs boson pair production with the full LSC run-to dataset in Atlas, given by Gabriel Palacino. And please start.
Can you confirm that you can see my slides?
Yes.
And hear me? Okay, 1 second. All right. 1 second, I'm trying to get this going. Okay, so I will be talking about searches for Higgs boson for Higgs boson pair production with the full run-to. Sorry, are you sure? Okay, cool. Now it's myself too. Okay. Okay, I'm gonna start again. So I will be talking about searches for Higgs boson pair production with the full run-to dataset in Atlas. So let me get going. I guess Higgs production is very well motivated within the standard model and also in Bsm scenarios. And one really good thing about this is that we can directly probe the self-coupling of the Higgs bosons. And this is the kappa lambda factor that you see in many of these Feynman diagrams. So this is a coupling modifier that we usually normalize to 1 for the standard model, but it pretty much controls the strength of these interactions. There is a number of production mechanisms in which we can study Higgs production. We have non-resonant gluon-gluon fusion, non-resonant vector boson fusion, and resonant production. And non-resonant vector boson fusion, it is also really good because it gives us access to another coupling, which is this quartic coupling, the di-Higgs, di-vector boson coupling. So there's been a number of results already released by both Atlas and Siemens collaborations covering a wide range of di-Higgs final states, but I'm going to be focusing on specifically 3 final states. We have di-Higgs to 4b, which is by far the one with the largest cross section. Then we have di-Higgs to BBWW, and then di-Higgs to BB gamma gamma. And these 3 final states I'm chosen here because they are the ones that have the full run-to data sets. And these specific analyses are the non-resonant di-Higgs to BB LNU vector boson fusion production of di-Higgs to 4b and di-Higgs to BB gamma gamma. So let's move on with the first analysis. This is non-resonant di-Higgs to BB LNU. So this is the first Atlas result in this specific channel. There's been previous searches on di-Higgs to BBWW using a different final state, the 1 lepton final state. So this is actually is the first one in Atlas. And this one has been optimized for non-resonant gluon-gluon fusion production. There are 3 different di-Higgs decay modes that contribute to the signal yield, the signal region. These are di-Higgs to BBWW, and this is the reason why I highlighted in the previous slide, because it amounts to 90% of the signal yield in the signal region. We also have BB tau tau, which is about 9%, and then BBZC, which only makes up 1% of the signal. The reason why these signal yields are distributed this way is a combination of the actual branching fractions of the different decay modes and also how the analysis was optimized. The dominant backgrounds here are top reduction and Z gamma in association with jets from heavy flavors. So let's move on to the analysis strategy. So one of the things that is used in this analysis that I think is very widespread, used in most of high energy physics analysis, it says, is the machine learning. So in this case, what was used was a multi-class neural network that was trained to classify 4 different processes, including di-Higgs, top, and Z2LL, where L stands for any of the lighter leptons, and then Z2 tau tau. And this neural network actually uses one specific characteristic of this final state, which is that it has 2 hemispheres. We have the BB hemisphere and the LNU hemisphere. And it was also trained using only the Higgs to BBW component, and this is because it actually has a larger branching fraction. The final discriminant is built using these 4 categories, and you can see it gives a very nice discriminating power between signal and background. So in terms of the results, so this analysis showed very nice improvements with respect to previous results in this specific channel. You can see here the search was performed on this DHH discriminant, and the sensitive region here is highlighted. But there are a few things to note. This analysis was not optimized for a kappa lambda scan. As you can see here, it can't really give you any constraints on whether this coupling modifier actually deviates from the standard model or whether it is consistent with the standard model. And it's still not sensitive to the standard model either. As you can see, the observed limit is 40 times the standard model prediction, although the expected was a little bit better at 29. Okay, moving on to the next analysis, we have a BBF di-Higgs 24B. So this one focuses only on vector boson fusion production, and this means that it is sensitive to the kappa to V coupling. Of course, there's also a big component of this vector boson fusion that is controlled by the kappa lambda coupling. But in this case, the GGF analysis are more sensitive. So what it is done here is that this analysis focuses mostly on extracting the kappa to V coupling. As usual, the characteristics of this final set is that you have two jets with a large opacity gap, and they're used to select the events. Because of the very large multi-jet multiplicity in this event, you have two main dominating backgrounds, and these are the multi-jet and all hadronic DT-var events. And there's been one very nice improvement to how this analysis is done, and is that the energy of the B jets is corrected using this boosted decision tree that was developed. And this results in a very nicely improved MBB resolution. And this is very important for this analysis because what you end up building here is pairs of B jets that would give you Higgs candidates. And this is what we're going to see in the next slide. So as I just mentioned, one of the things that has to be done here is define these Higgs candidates. So you start from this 4 B jets, and then you have to figure out what's the right combinatorics in order to get the right Higgs candidates. So in principle, what you would like to have is two Higgs pairs, pairs of B jets that are actually consistent or as close as possible to the mass of the Higgs. Of course, this is never going to be exactly that, but then what it's done is that then the distance, the two pairs that have the shortest distance to this diagonal that is defined here by this DHH, which is the distance to the diagonal in the di-Higgs candidate mass plane. So the ones that have the shorter distance are chosen as the two Higgs candidates. And it is in this Higgs candidate mass plane that the signal validation region and control regions are defined, as you can see here. And specifically, the signal region is defined using this oval shape that you can see at the top. And then the analysis is performed using the 4B invariant mass phase space. So moving on to the results. So in terms of the resonant search, two sets of limits have been derived. One for this one specific narrow fixed width of 4 GeV. So this is a very narrow resonance. And then we have the two Higgs double model type 2, in which the weight of the resonant mass goes from 10 to 20%. And then I guess the more important or the more interesting part for many people is this kappa 2V exclusion. So we can see that this range goes from minus 0.76 to 2.9. And there are 2 points to make here. The first one is that kappa 2V equals 0 is not yet excluded, which means that we cannot exclude that this coupling doesn't happen. And then the other one is that, as you can see, this search is not yet sensitive to standard model. So we still need to work towards collecting more data and probably improving analysis techniques. Okay. The final analysis that we have here is di-Higgs to BB gamma gamma. So let me move on to, oh, it doesn't respond anymore, okay. So in this analysis, both gluon-gluon fusion and vector boson fusion have been considered as signal, but the analysis has only been optimized for GGF. And this is done in order to increase the sensitivity to kappa lambda. And as usual in any Higgs to gamma gamma search, what we search for is a pair of photons that have an invariant mass that is consistent with that of the Higgs boson. This analysis is, I guess, the three and the other two analyses that I've already presented, uses extensively machine learning or multivariate techniques. I'm going to go and explain what they do with that in a few seconds. But one of the key improvements in this analysis is that they try to mitigate the detector resolution effects by redefining the invariant mass of the BB gamma gamma system. And the way they do that is that they subtract from the invariant mass of the BB gamma gamma system the mass of the BB and gamma gamma systems individually, and then add 250 GeV to it, which is roughly twice the mass of the Higgs boson. And what you can see is that in particular for the resonant masses, the resolution is improved significantly. So this is something that worked very well for this analysis. So let's move on to the resonant selection. So non-resonant selection. So in this case, there were two BDTs that were implemented. There's one for low mass, which covers the range from 350 GeV and below. This was trained on kappa lambda equal 1, which is the standard model. And then there's a high mass region BDT that covers 350 and above. And this is trained on kappa lambda equal 10, which is harder than the standard model processes, and such. It's better for the high mass region. These BDTs exploit kinematics, the kinematics of the signal in the background and some B-tagging information, and you can see how well it discriminates signal versus background. And the final analysis in both cases, the resonant and non-resonant, is performed in the diphoton mass continuum. Now moving on to the resonant selection, this one uses as well two BDTs, but in this case, the BDTs are used in a different way. They're used to separate two different classes of backgrounds. We have the gamma gamma background, which comprises gamma gamma and gamma gamma TT bar. And then we have the single Higgs background, which is ZH and TTH. These two scores are combined in some sort of quadratic way so that we get a final BDT score, and you can see it here. And there's one issue here that we need to solve, and is the fact that we have limited limited mass points for the different resonant samples. So in order to be able to maximize them, what is done is that all the signal points are reweighted on an event by event basis in order to match the MBB gamma gamma distribution of the background, such that the BDT training is independent of the resonant mass. The BDT performs fairly well, as you can see here at the bottom. And then we can move on to the results. So I guess the two main points to make here is that the limits on the di-Higgs non-resonant production cross-section, the observed limit is at 4.1 times the standard model prediction, and the expected is 5.5 times. This is an improvement by a factor of 5 with respect to the previous results, which you can find here. And this is due to two things. The first one is that there's a factor of 2 from luminosity, and then the rest comes from the improved analysis techniques. And in terms of the kappa lambda constraints, the range have shrunk by a factor of 2, and now it is limited to minus 1.5 to 6.7. Okay, so I guess I'm gonna move on to my summary. So I just wanna mention two things here in the summary. The first one is that we've done a lot better than was ever expected from the Atlas experiment or from any experiment. I mean, I guess both experiments have done very well in this sense that we've closing in on standard model. So we're doing much better than was ever expected. And we continue doing so because we have people that are working very hard to improve the analysis techniques and be able to extract as much information as possible with the luminosity that we have. The second point is that you should stay tuned because we have in the future, we will have new results coming with the full run 2 data set. So at the moment, we only have 3 searches, but there will be a large number of them coming out in the next 12 months, and including a combination that will supersede this combination with the partial run 2 data set. So that's it for today. So thank you very much.
Thank you. So you finished in time. So we can have 1 or 2 questions. So this system is a webinar, so you can not directly tell us, I can give you permission to say. So let me know if you have any question. You can raise a hand, or you can leave a message in the chatting room or Q&A in the room, Q&A window. So, so I have a question. So you said you are using the machine learning technique for your analysis. Can you say a bit some specific tool and framework?
Sorry, so do you want to know about the specifics of the machine learning techniques that were used in which analysis?
Right.
In which one of the three analyses? Because, for example, the first one used and the first one is Higgs to BBLNU. This one used Keras with a TensorFlow backend to develop this neural network. About the architecture of the network, I will have to refer you to the paper because I don't know exactly how it was done. The next one, which is the Higgs to 4B, in this case, it was a BDT that I believe was implemented using TMVA. And in the last one, which is also two types of BDTs, I believe they were also implemented using TMVA.
Okay, thanks. Any other question? Okay, it looks no. Okay, thank you, Gabriel. So we will have the next talk. So next talk is searches for Bsm Higgs at CMS, given by Gumo Ruth. Can you share your screen?
Yeah. Hello. Can you hear me?
Yes.
Okay. So let me share my screen. So can you see my slides?
Yeah, I can see where. Please start.
Yeah. So I will be talking about the searches for Bsm Higgs at CMS and we have CMS collaboration. So let me go to next slide. So for the motivation of our okay, so for the motivation part for the different Bsm searches for Higgs is as we already know that the object standard model Higgs boson at a mass of 125 GeV may not be the only one in nature, and there the extended H sectors are coming off, and these are strongly motivated because there are some phenomena like hierarchy problem, neutrino oscillation, baryon asymmetry, nature of dark matter energy could not be explained by standard model. So some additional Higgs bosons are also predicted by some extended parameter space of Bsm theories, like the 2x doublet model and next to minimum supersymmetric standard model. Accordingly, we can have the neutral Higgs bosons and also the charged Higgs bosons, singly charged or double charged Higgs bosons. And in the neutral Higgs boson, we can have light neutral Higgs bosons and also the heavy nuclear neutral Higgs bosons. So many of the searches have been performed in the Bsm Higgs sector at LHC with a full run to data set and that covers a wide mass range. And I will be showing a few of the results that has been carried out using the full run to data set. Let me move on to the next slide. So these are some latest Bsm Higgs searches at CMS. So we have heavy neutral Higgs boson searches in which decays to observed standard model Higgs boson and also the another Higgs boson. And also there are the charged Higgs boson searches which include single charge Higgs bosons, decays to a charm core and the strange core, and also in other channels like in there also single and double charge Higgs bosons which decays to vector bosons like WZ and also WW. So I'll be mostly discussing about these three results. So let me go to next slide. So of initial first result is the search for the heavy neutral Higgs bosons in the BB tau tau channel, and which this is the first BSM search for a heavy neutral Higgs boson, which decays to a standard model Higgs boson and another Higgs boson of mass which is less than the mass of heavy Higgs boson minus the mass of standard model Higgs boson. And the standard model Higgs boson decays to a pair of tau leptons, and also the other scalar decays to a pair of big quarks. And the analysis has been performed using the full round 2 data sample. So, and for the final state tau leptons, the tau pairing has been performed using electron tau lepton final state, muon tau lepton final state, and a pair of tau lepton final state. And for the VZ selection, to 1 or 2 VZs have been considered. So for the offline event selection for targeting these three categories, so we have the selection on the transverse momentum of electron or muon, and also the transverse momentum of hadron, which are basically according to the online single electron or single muon trigger. And also for the isolation, for the isolated electrons and muons, isolation codes have been applied also. And in the event classification process, event classification and the signal extraction, these are performed using the neural network-based multi-classification techniques for this analysis. So accordingly, 5 event categories have been chosen. So using a particular heavy mass of Higgs boson 500 JeV, and also the mass of the scalar, which is in between 100 to 150 JeV. And as you can see in the right bottom plot, there is a neural network output distribution of the mu tau signal final states. So yeah, where all the signals and backgrounds have been considered. So let me move on to the next slide. So here, so the for this heavy neutral Higgs boson, the mass range have been explored from 240 JeV to 3000 JeV, and also the mass of the additional scalar, which is considered to be 60 to 200 2800 JeV. And here, so the no signal has been observed in this mass range. So a 95% confidence level upper limit has been obtained on this search process. So at 240 ZIP, lower search limit, 240 ZIP, we have 125 femto1. And at the higher limit, 3000 ZIP, we have 2.7 femto1. And these limits are also interpreted in the near to minimal supersymmetric standard model. So as you can see in the right plot, so this is a 2D plot of heavy mass with the light mass. So with here, it has been constrained for masses of the heavy mass from 400 to 600 JeV, and corresponding to the mass of the light scalar, which is from 60 to 250 JeV. Okay, so let me move on to next slide. So now, so another Higgs search, another Bsm search, which is a single charge Higgs boson. This is also a fast search at LHC, which is performed in the process of top quark trap production, in which the one top quark decays to a charged Higgs and a big quark, and which subsequently decays to a charm quark and stream quark, and the top quark decays to a big quark and the W version. So this in this analysis, the final state contains the charged leptons plus the missing transverse energy and at least 4 jets. In phase, 2 V jets have been considered and 1 CZ and one light flavored jet. And the search sensitivity of this analysis is enhanced by choosing 1 V jet, which is stacked to charm jets. And the muon and electrons in the final state have been chosen with PT greater than 2630 zip within the acceptance eta, and the isolation codes for muon and electron have been used in the barrel in-cave region. And for the jets, the jet PT greater than 25 zip, and for mid missing transverse PT greater than 20 zip. So if we move on to next slide. So this analysis has been considered 2 channels, the muon plus Z channel and electron plus Z channel, and no significant excess have been observed. No significant excess beyond the standard model prediction is found. So an exclusion limit, a 95% confidence level, and the top quark decay have been given by assuming the branching ratio of charge 6 to charge 1 strain square is 100%. And the mass range explored for this light charge 6 boson is from 80 to 160 Z. And for these 2 channels, muon plus Z channel, the limit is from 2.44% to 0.32% in this mass range. And for the electron plus Z channel, it's from 2.77% to 0.26%. And by combining these 2 channels, we have 1.68% to 0.25%. So let me move on to next slide. So there are another charge Higgs boson searches also have been performed in CMS using the vector boson fusion processes. And here the charge Higgs boson is produced from the vector boson fusion, and it also decays to vector bosons from like WZ and also the WW. And this is according to the model Georgi-Wakek model. And this analysis also has been performed using the full run-to data of 137 inverse chapter 1. And since we have the final states involves leptons, the search is also performed in electronic decay modes, where we have neutrinos and leptons. So in the offline event selection, we have the WW and WZ. So the leptons, are chosen with PT about 25 to 20 zip. And in the WZ case, the 3 leptons chosen with PT greater than 25 and greater than 20 zip. And the invariant mass of 2 leptons is chosen from 20 zip, and the missing PT is chosen from greater than 30 zip. So, and using this selection criteria, so let me go to next slide. So the analysis uses discriminant between resonant signal and non-resonant background processes. So there is a divergent transverse mass, which is in this expression. And the final discriminant is a 2D distribution in terms of the mass of dized invariant mass and the transverse mass of diversion. So in terms of different bends, like for example, for WW signal regions, there are 8 bends in transverse diversion mass and also 4 bends in mass of dized invariant mass. And similarly, for the WZ signal regions, there are 7 bends in transverse mass, divergent transverse mass, and 2 bends in dized invariant mass. And in the control regions, there are 4 bends in dized invariant mass. And these are the simultaneous fit has been performed using the signal and backgrounds in these different bands. This can be seen in this figure. Okay, so let me move on to next slide. So here, so these are the limit plots for this analysis. So here, as you can see, no significant excess beyond the standard model prediction is also found. And that using charge Higgs boson mass explode for this analysis is from 200 to 3000 J. And the exclusion limits have been obtained at 95% confidence level on the single charged Higgs boson and for the double charge Higgs boson in the VVA production process. And so in the George-Markov model, the observed limit excludes the George-Markov model in the values of greater than 0.2 to 0.35 for the charged Higgs boson mass ranges from 200 to 1500 J. So these are the results that I have. Let me go to the summary, please. So the extended Higgs sectors in the BSM theories are strongly motivated to give additional explosions. So I have presented some of the latest BSM Higgs surges using Round 2 data at CMS. And there are more analyses which are in the final stages using Round 2 data which are coming up, and we can have more results which will be available soon. Thank you.
Thank you very much. So we can have one or two questions. I gave you the permission to talk via Zoom webinar, so you can say something directly if you have any question. No question? Yeah, maybe each very clear. So yeah, let's move on to next talk. Thank you again.
Thank you.
Kumar. The next talk is searches for lepton number violation at GMS, given by Barun Sama. Please start. I will give a notice in 12 minutes.
Okay. Hi, I hope I'm audible and my slides are visible. So, okay, I'll be talking about the lepton flavor violation searches at the CMS experiment. So starting with a very quick motivation, we know we have 3 generations of quarks and leptons, and they do change generations, and so do neutrinos. So how do we know about neutrinos that they change generation? It comes from the fact that neutrinos have non-zero mass. They are not really massless, that they change flavors. And despite all the precision that we know of the standard model of the particle physics, it deals with a lot of symmetries, but there is still no fundamental law why there should not be any violation to the lepton flavor or lepton number. So that's what I'll be talking about. There are different searches that are done by at CMS to probe lepton flavor and number violations, and using the proton-proton collision data at 13 TeV. And for the searches that I'll present today, at least one search uses the entire full run-2 data, which was done from 2016 to 2018 and corresponds to 137 femtobarn of data. And rest all are done with 33 femtobarn of data, and they are being done with, updated with the full run-2 data. Okay, so I'll be talking about 4 different decay modes where I'll talk about the lepton flavor violations, starting with the Higgs to E tau mu tau and tau to 3 mu final state, then the production of Majorana neutrinos and heavy resonances decaying to E mu final state. So starting with the first one, where we try to look for standard model Higgs decaying to either E tau or mu tau final state. We know that fermion masses in the Standard Model are proportional to the vacuum expectation value of the Higgs, and they couple to Higgs by Cover-Met couplings. And in the Standard Model, we just have the diagonal terms, and the non-diagonal terms are set to 0. But there is no reason why we cannot have the off-diagonal terms. So there are different beyond Standard Model theories that allows for off-diagonal terms. So in this particular lepton flavor violating decays, we take the Higgs boson decaying to E tau and mu tau final state, which can be a good probe for beyond Standard Model physics. We do not consider E mu final state because the mu to E gamma the null results from mu to E gamma puts a very strong constraint in Higgs to E mu final state. So we do not consider that in this study. And as is can easily be seen that this analysis is categorized broadly into mu tau and E tau final state, and it's further categorized based on the decay of the taus, which is leptonic and hadronic. So we have 4 broad categories of Higgs to mu tau, leptonic and hadronic decays of taus, and then E tau hadronic, E tau leptonic. So for the signal, we take mostly the glucose Higgs and vector boson fusion production of the Higgs because they are the dominant one. And the leading backgrounds for this final state comes from the Z plus jet and misidentified leptons that are estimated from data directly. And the subleading backgrounds are taken from the Monte Carlos. And to enhance the sensitivity based on the different Higgs production mechanism, the events are further categorized into 0 jet, 1 jet, and 2 jet categories. And then the 2 jet is further classified based on the invariant mass of the 2 jets. And once the categorization is done, we have several inputs that are given into the Booston decision tree, which is used to extract the signal. And once the signal is extracted, that's passed maximum likelihood fit is done based on the discriminator of the Booston decision tree to get results. So here I show a collinear mass distribution. The collinear mass is defined as the visible mass of the E tau or mu tau system. Here I show the E tau hadronic category, where you can see the blue is the Z to tau tau background, and which is the leading one as expected in the E tau final state. And a very good agreement can be seen between data and the Standard Model predictions. And on the right-hand side, you can see a list of the inputs that goes into the boosted decision tree. Just to mention here that one of the important variables are the transverse mass of the lepton and met system, be it E tau or mu tau, and the collinear mass. And on the bottom is the output BDT discriminant that we get from the boosting decision tree. And here also you see the signal lies in the high BDT discriminant region. So we need to have some excess of events here to see some hint for the lepton flavor violating decays. But we see a very good agreement. So there is no signal. So there is no evidence for lepton flavor violating decay of Higgs boson. And thus we go ahead and set limits on the branching fraction of the Higgs decays. So on the top, the first plot on the left shows the branching fractions of Higgs to mu tau for all the different categories that we have. The top 4 are the mu tau for 0 jet, 1 jet, and 2 jet categories, while the bottom are mu tau leptonic channel. And on the exact bottom, at the bottom shows the combination of all the 8 categories, and we set a limit of 0.15% as which is the same as we expect in this decay. And if you look at the E tau, where we have the combined result, I show the combined result, and where there also you see an observed 0.22% as compared to 0.16 expected. Based on this branching fraction limits, these are translated into the limits on the Yukawa couplings for the off-diagonal Yukawa terms. And you see here the observed and expected are almost and the same for mu tau. So they're just shown here with the black curve, and the green and yellow are the 68 and 90% confidence level intervals, and they are also, the limits here are also compared with the tau to mu gamma and tau to 3 mu decays, and we see the limits for the Higgs to mu tau are very strict, from it's about 1.11 to about 10 to the minus 3%. So that's very stringent limits that we get imposed on the Yukawa couplings as well. So moving to tau to 3 mu decays. So, I'll be revolving around the neutrino oscillation. So the observation of neutrino oscillation does not just proves that the lepton flavor is not conserved, but they also provide a mechanism through neutrino loops for the lepton flavor violating decays, albeit extraordinarily small branching fractions, but they do provide a mechanism to probe this. So this analysis is also done by LHCb and Atlas, but for LHCb, they only consider the heavy flavor hadronic decays to produce taus, and while Atlas just considers the W boson decay to produce taus. So but CMS considers both the production modes for taus and then combine results to get the final results. So for the heavy flavor, taus produced by the heavy flavor are large in number. So basically it's a dominant production mode for taus, but it also disadvantage that it also have a large background. While the taus produced by the W bosons, they are isolated with large PT, and they are less, do have less background. So it's a pretty clean channel. So results in this are, the data is triggered by at least 3 muons. So and the signal region is around the tau mass. So the invariant mass of the 3 muons is required to be between 1.35 to 1.8 GeV. So that's the window that is considered for the signal region. And to estimate the background, they are estimated in the side band, so from greater than 1.8 and below 1.75 GeV. So like the previous analysis here, also the signal is separated from the background based on the training done on the boosted decision tree. And to enhance the sensitivity, both the different categories, the heavy flavored hadron decay and the W boson decay, are analyzed separately. And in the heavy flavor, they are categorized based on the per event prime muon mass resolution and on the PDT score. So we have about 6 categories for heavy flavor because this is a statistically rich region, so we can afford to have more categories. While for the W boson decay, which is statistically limited, we just divide the analysis, categorize the events in the barrel part of the detector and the end cap part of the detector. As just to list some, because this analysis uses the 3 muons, so we use the informations on the trimuon vertices to feed to the boosted decision tree. So the angular angles between the trimuon momentum vector and the vector connecting the primary vertex and the 3 muon vertex, it's a very important variable. Then the transverse impact parameters of the muons with respect to primary vertices and the isolation variables. They are really important inputs to the BDT that helps separate signal from the background. And based on the simulation, we see that the tau leptons in the data samples are mostly produced by the D decays. That's the 75% of the times the tau leptons we are getting are from the D decays. And even in the Ds, it's mostly from the DS and not from the D plus. And the rest 25% comes directly from the B decays. So on the right-hand side, you can see the invariant mass distribution of the 3 muons for one of the categories. As I mentioned that we have about 6 categories. So here, just for one category, you can see the data, and that's fitted with the background only FET. And to extract this background only FET, it's extracted from the DS decay. So on the left, you can see the invariant mass of the mu mu pi coming from the ds, and you can see the red curve is for the Ds, which is about 75% of the total background, and the blue line is the background, which is matching the data. So we have a very good agreement on between data and background. And after combining the two channels, the hadronic and the Ws, we put and observed upper limits on the branching fraction of tau to 3 of 8 into 10 to the power minus 8 at 90% confidence levels, as expected to 6.9 into 10 to the power minus 8. So I must tell you that this sensitivity is very much compared to the limits that we get from Babar and LHCb, but they are still a factor 4 away from the current best that are given by the Bell experiment, which is very sensitive to this surge. So moving from the 3 tau to 3 muon to the heavy Majorana neutrinos. So again, we know that neutrinos are massless, and one of the leading candidate to explain the massless phenomena, massive phenomena of neutrino is the seesaw, the well-known seesaw mechanism. And this mechanism postulates the existence of a heavy Majorana neutrino, and this mechanism just postulates this heavy neutrino states without postulating any additional vector boson. So that's good thing about this model. And why the neutrino masses are suppressed is because you can see here the masses are related with the masses of this heavy neutrino. And that's why we call generally the heavy Majorana neutrinos, because they suppress the neutrino masses. Vy is the Yukawa coupling, and V is the vacuum expectation value of the Higgs. And in this search, this Feynman diagram is considered, and if you see here, W plus decaying to a heavy neutrino and a lepton, which further decays to a W and L. So there can be different final state, but the advantage of this particular channel is that we have two same sign leptons produced in this final state along with two jets. So this helps us restrict the background we have, because it's very few backgrounds will have the same sign lepton in the final states. So based on this results, we put a limit on the mixing matrix of the between the lepton and the Majorana neutrino using a cut and count method. So to select events, as the Feynman diagram suggests, that we simply suggest two same sign leptons with an invariant mass of greater than 10 GeV and away from the Z mass window. And the events are vetoed if there are additional leptons and there are no jet in the event. So there's at least one jet that's required. And like other previous analysis, this analysis is also categorized into two regions, the low mass region and high mass region. The low mass region is basically when the mass of the Majorana neutrino is less than the W mass. And while for the high mass region, we require it to be greater than W. And they are further categorized into two categories based on the number of jets we have. One important thing to note that in the high mass region, we require that there is at least one AK8 jet. AK8 jet is the jet reconstructed using anti-KT algorithm of the radius 4, while the AK4 are the anti-KT jets with a cone radius of 4. So if you see on the left-hand side, when the Majorana neutrino mass is less than W, we can have the mediator W produced on shell and then decaying to V and U. So here the mass of the LL and W jet. So basically this LL and 2Q mass is required to be less than 300 GeV, because we have the on shell W being produced here. And on the right-hand side, we have the other W coming from the Majorana neutrino to be on shell. So this N is greater than. And the leading background, so we have very few backgrounds in this kind of final state. So they are broadly categorized into three categories. The green one here list is the prompt lepton background, which is contributed by the dibosons, mostly ZZ, W, WW or WZ, while the blue is the misidentified lepton background, which is dominantly contributed by V plus jets and some other small contribution. And the last, the least contributing of all is the measured sign assignment, which is because we have a very nice tracker, and so there's very less probability of assigning a wrong sign to the particles, to the leptons. Okay, so based on, as we have a very good agreement, we do not see any excessive events, we go ahead and set limits, and the limits are set as an upper limit on the mixing matrix between the standard model neutrino and the Majorana neutrino in the context of type 1 seesaw model, and they are set as a function of neutrino mass. So with this particular search, the search is sensitive to masses of about from 220 to 1.6 TeV, and this result is just with 36 femtobarn of data, and the new results are coming, so stay tuned for that. So moving to the last search, where I'll be talking about the heavy resonances to E-mu final state. So it's a generic model independent search for the existence of a heavy particle that can undergo lepton flavor violating decays. This search is also done at 13 TeV with 36 femtobarn of data. It's a very generic search where we try to look for, it's a S-channel search, so we can have look for a bump over a falling standard model background in the invariant mass distribution. So here we have on the x-axis the invariant mass of the E-mu system. So the results for this search are also interpreted into different theory models, namely our parity violating SUSY, where the both lepton flavor and numbers are violated at the lowest bond level interaction between the new fermions and their superpartners. And all the RPV couplings are assumed to be zero except for the lambda 123231 and these couplings. And the neutrino decays to E-mu, it's an important aspect that neutrinos decays to E-mu promptly, and they are not assumed to be long-lived. There is a separate dedicated search for long-lived particles because they have different triggers and many other factors included. The other search is the quantum black holes. So this theory provides the possibility to produce microscopic black holes at LC, where these quantum black holes are non-thermal and they are expected to decay predominantly to just to a pair of particles. There are models which predict that the quantum black holes can decay to multiple particles, but this particular model restricts them to decay predominantly to a pair of particles, and they are assumed to be spin zero and colorless. The last is the Z prime, which where a new particle is produced with the addition of extra U1 gauge symmetry, and we have a massive Z prime vector boson. And here the decay of the LFE to E-mu final state is set with a branching fraction of 10% and width of about 3% to that of the mass of tau pair, TT bar. So this slide I show the invariant mass distribution of the E-mu system, and you can see it's a nice falling background spectrum, and the data follows the background. So we do not have any excess. And that's just to see that how the background matches with the data in different mass windows. They are tabulated with different selection on the invariant mass distribution of the E-mu system. And we see in all categories, there is a very good agreement between data and the background. And the results are then for each theory models are interpreted separately. Like on the left-hand side shows the parity violating SUSY model, where you have the limits in terms of coupling versus the mass of the neutrino, and for different settings of the coupling param ranging from 0.07 to 0.007. And on the right-hand side, the limits are sent on the branching fraction of the quantum black holes as a function of the mass of the particle, and you can see we exclude different mass limits for different large extra dimensions, like 5.3 limits for 4 large extra dimensions. The right-hand side shows the limits on the Z prime mass, on the branching fraction, cross-section time branching fraction on the Z prime mass. So that was it. So CMS performs several searches for lepton flavor violating in different channels. We haven't found any evidence, but put very stringent bounds on different parameter space on different models. So stay tuned for the upcoming results with full Tron2 data for the analysis which are just well. Yeah, that's it. Thank you.
Okay, thank you. Yeah, very comprehensive talk. So, any question? Actually, I have a question. So, for tau 2-3 muon analysis, what do you know what exact the trigger threshold? I think this is a trigger is main essential component for this analysis.
Sorry, the trigger is?
Yeah, the trigger threshold. I mean, you require 3 muons.
Trigger
right?
threshold. I don't remember the trigger threshold, but we have a combination of trigger. Like there is a very low threshold trigger which requires 3 muons, but there is also a combination where it just requires 2 muons and with some tighter selection. So I don't remember the exact thresholds now.
Okay. So and do you know what is planned for learn 3 for this analysis? Do you have any plan to include some specific trigger for this this channel for round 3?
Yes, I think there's already ongoing with the run 3. We'll see if some dedicated, because right now a combination of triggers are being used. If there are discussion ongoing, if a dedicated trigger can be included for this particular analysis.
Okay, thanks.
Yeah, because the menu is not yet final for run 3. It's being the planning is on the way.
Mm-hmm. Any further question to Varun? Yeah, I have one question from Wonsang Zhou. Can you? Yeah.
Can you hear me?
Yes.
Okay. Actually, I'm very sorry for giving late question. Can I give a question to Andreas?
Yes. Yeah.
I just put my question on the chatting.
Yeah, I think you can do it. Because we had no question for Andreas.
Yeah, go ahead.
Okay, thank you. Actually, you introduced the deep AKA model in search for dark matter from the GH production, focusing on the features ISRZ versus FETZ from Z-boson decay. Especially, I have a question on invisible Higgs searches via the GGH channel. Actually, as you introduced, the VVF channel and GH channel are driving channels. And my question is that, is there any possibility yet or plans at CMS Atlas to build and deploy a discriminator featuring on the difference such that the ISRZ, which is narrower, came from the quark jet from mainly the electroweak vector boson production versus ISRZ, which is broader, mainly came from the gluon jet from gluon fusion process. So this is my question. And actually, as you know, so such a difference is well known already and can have a potential to give a significant improvement on invisible Higgs such as via gluon fusion channel. So I have a question on the something like that. And I also wanted to raise your interest on the possibility.
Thanks for this question. I think it shows that you've thought about this in detail. So I think we're already doing this. The fat jet discriminator is the neural network. You can look at the paper. If you just look for DeepAK8, you should also find it on the web. It is fed with information of basically all the particles in the fat jet. So the properties of each of the subjets are taken into account. So the fact that each of the subjets looks quark-like as opposed to gluon-like is implicitly already taken into account. I can't tell you how much of the discriminating power comes from that. I would think not too much, because quark-gluon discrimination is always kind of fishy, but I think this is taken into account for whatever it's worth. And if you're thinking about resolved jets rather than fat jets, then that is currently a little less interesting, simply because we have to go to high PT anyway for triggering. So the slow PT resolved cases are not really the driver, but we also do that, but I think we're not currently looking at quark-gluon discrimination.
Thank you for the answer. Actually, as for the PT of jet, as far as I know, as the PT of the jet increase, the discrimination power, especially the difference between the product, the quark jet at radius of quark jet and the gluon jet becomes larger. So I think features can be available for several, so broad range of PT of ISR jets. Okay, thank you for your answer. If there is time, can I ask one more question to the second speaker?
Yeah, go ahead. Quickly.
Okay. Thank you for your nice talk. Actually, you introduced dikes such as for BB, LNU channel. Then in the features you show there, it composed of various features, PT or some angular variables, and there appears as MT2 variables. Now I'm curious if you are also using some feature variables. Actually, the decay topology has some resonant particles, the Higgs and W boson, but partly it can be off shell. So there is some good researches which try to build a duality discriminator using some reconstructed masses. So I'm curious why such, and the research report that if one use such kind of reconstructed masses, then the performance improved significantly. So I'm curious if you already tested such a reconstructed masses, or some likeliness, like calmness or fixedness, such kind of variables.
Right. So I guess there are, I could refer you to the Higgs prospect paper, where they have actually investigated how the sensitivity of the analysis, especially BBWW, could be improved using thickness and toughness. In this analysis that I'm showing here, it was not used. It was investigated whether it could be used, but it wasn't. Now, regarding the reconstruction of the masses, it has always been an issue because we have one off-shell W. So the idea here is to try to avoid, or at least what we're planning towards the future, is to try and avoid the reconstruction of these masses, so that we feed our machine learning methods with more lower level features, so that we don't have to fall into inefficiencies due to the badly reconstructed off-shell W, for example. So this is something that has been done, and it is it's being done towards the future publications.
Okay, I see. Thank you for your nice talks and the answers.
Okay, thank you for the answers. So let's move on to the last talk for this session. The last talk is results and future plans of model experiment given by James Pinford. Can you share the screen and yeah, please start if you are ready.
Oh, can you see the screen?
Yes. Yeah, I will give some notice in 12 minutes.
Okay.
Then you can expect 3 or 5 minutes left.
Okay, thank you. So I'm going to tell you about the results and future plans of the metal LHC experiment. It's not like the other experiments you just heard about. This is what's called a dedicated search experiment. It was the first dedicated search experiment, the LHC. Why do we need a dedicated search experiment? Well, one of the reasons is we haven't seen any new physics yet from the LHC. Now, what is the reason for that? It could be that new physics is, should we say, beyond the bounds of the energy scale of the LHC. It could be a lot of other reasons, and the dedicated search people think that it could be that maybe we are not sensitive to the new physics. Well, so the approach of the metal map experiment is to look for new avatars of new physics, like highly ionizing particles, HIPs, milli-charged particles, MQPs, and long-lived particles, very long-lived particles, in a way that is complementary to the general purpose LHC detectors, ATLAS, and CMS. So we look for very highly ionizing particles that are greater than 5 times that of a standard relativistic charged particle, very long-lived neutrals, you know, that can have lifetimes up to kilometers, feebly interacting particles with tiny standard model interactions or charges, for example, that can be as low as 1,000th that of an electron, or very long-lived charged particles, lifetimes up to 10 years. So this is the idea here, is to look for things that the main experiments would find very challenging. So this is the metal detector that took data at run 2 and run 3. It's clustered around the velo detector at point 8. This velo detector, of course, is LHCb detector. And these detectors around here, the nuclear trap detectors and the trapping detectors, all deployed around the velo detector, as shown in this diagram, are our ways of checking for new particles. The good thing about this approach is we have a permanent physical record, because the nuclear track detectors are like a emulsion or a film or a camera photograph, if you want. There's a permanent record of highly ionizing particles that may traverse these green planes. We also, in these beige planes, beige boxes here, can trap highly ionizing particles. Here we see a monopole that's trapped next to the nucleus of aluminium. It's got about 1 ton of aluminium trapping devices, so we can trap new detectors. We also have rather conventional time pix arrays in order to measure beam backgrounds. And the very nice thing about this experiment is it doesn't need a trigger, and there are no standard model physics backgrounds. There are, of course, backgrounds that can muddy the waters, that can fuzz the film, but nothing that can cause a fake signal. So here are the physics issues for the metal detector at the LHC in run 2 and run 3. We can look, for example, dions and monopoles. Monopoles, if you want, are our Higgs boson. We know that LHC was made to detect the Higgs. We have sort of, our first baseline process is the monopole, but we can also look for dions, electroweak strings. Sorry? Sorry? Okay, D particles, electrical charges. We can look for Q-balls and strangelets, slow-moving SUSY particles, stable microscopic black holes, etc. So that is the main physics topic of metal. It's looking for highly ionizing particles. And what's happened so far We see here the limits that we placed. Obviously, we haven't discovered the magnetic monopole, but if we have magnetic charge, which is in units of Dirac charge against excluded magnetic monopole mass, we can see that at run 2, we've reached up to around about 2 TeV. Our only competition at the moment is at the ATLAS experiment. This is Drell-Yan produced particles. If we go to run 3, and we're planning now to run again at run 3, we see that we can exceed the reach of the ATLAS detector at that stage. ATLAS can only reach to a charge of 2, whereas we can reach to charges of up to 6 now. Of course, we also look in, uniquely look in the gamma-gamma process, and we can see that when we look at gamma-gamma production of magnetic monopole pairs, we exceed the reach of the ATLAS detector. So that will be one of the big issues of the of run 3 for us. We also have made the first direct search for dyons. These are Schwinger's hypothetical particles which have electric and magnetic charge. And we can see the range of exclusion here for various charge, electric charge, magnetic charge combinations. GD is the magnetic charge. And here we have the electric charge on the x-axis and the excluded mass on the y-axis. And we exclude masses up to about 3 TeV and charges up to about 200 E. And magnetic charges up to 5 GD. Another very interesting paper that is really just near submission is the search for magnetic monopole pairs in heavy ion production. And I'm sure you'll know that in heavy ions, you can create fields that the highest fields in the universe. For example, we can create in heavy ion collisions at the LHC fields as high as 10 to the 16 power 16 Tesla momentarily, whereas magnetars in the universe, these are various cosmic bodies, can only get up to about 10 to the 11 Tesla, and that's about the highest you can get in the universe, except for where you have these heavy ion collisions. And we're looking for monopole production via Schwinger mechanism, which essentially is an analog of E plus E minus pair production in the presence of an extremely strong field. We have monopole production, pair production in the presence of an extremely strong magnetic field. And what's important about this approach is there's no exponential suppression for finite size monopoles. If we have for example, in the previous searches, if the monopole had a finite size, you would expect the cross-section to be exponentially suppressed. And also the cross-section calculation for monopoles, Drell-Yan production, for example, which is a normal way of searching for monopoles, has a problem with non-perturbative couplings, which is not the case in this analysis. As I say, this paper is near submission, and we expect it to be out within a few months. Another very interesting search that's going to continue a lot in run 3 is the search for, should we say, slowly moving ordinary singly charged electric particles, which are sort of long-lived. So we've looked at some SUSY particle production. Here we have gluino, where one of the gluinos goes to 2 jets and a neutralino. The neutralino decays to a STAU and a tau. If the neutralino is long-lived and the STAU is heavy enough and slow-moving enough to give us a signal in our nuclear track detectors, we can make an identification of this process. And if we look at the C tau for the neutrino here and the mass of the gluino on the x-axis, this is GeV, we can see the search results for these various contours of the search results using SUSY, and this is the search result from a CMS analysis. And you can see that we can help to push the results to higher C taus for the neutrino, and so add to the search for supersymmetry at the LHC using a completely different detector with completely different systematics and pushing the limits in a new way on the exclusion plot. So now we move to what we're going to do for run 3 and beyond. And this then it becomes a metal MAP project, where MAP stands for Metal Apparatus for Penetrating Particles. It's going to be deployed in the UGC1 gallery here, which is, and here we see the LHCb intersection region right there. And the MAP detector will be deployed about 55 meters away from the intersection point, the LHCb intersection point at which metal is surrounding, as shown here. And this is a plan view of the region. This is the UGC1 gallery. This is where the metal detector is and where the velo detector is. And we place the detector here in the UGC1 gallery. The detector consists of an inner core, which detects milli-charged particles, and an outer sort of Russian box. That means it's boxes within boxes of detectors that inspect this decay zone here. So particles, neutral particles coming in here will pass the veto and decay in this zone and be detected in the walls of this box. By the way, we've left the lid, and you can't see the floor, and we've left the lid off so you can see inside. Phase 1 of metal map for run 3 will have the redeployed metal detector that I've just been talking about, and this MAP 1 milli-charged particle detector that I'll tell you about in a minute. That's going to go in spring 23, and the redeployed metal detector in spring of 2022, assuming that the LHC opens up as advertised. Phase 2 will deploy MAP 1, which is this LLP detector, this Russian box detector, around the phase 1 milli-charged particle detector. We'll deploy that for run 4 probably, and for phase 3 we'll deploy MAP 2, which is an extension of the long-lived particle detector down the UGC1 gallery. We'll deploy that for run 5. So let's look at what's happening for run 3, 2023. This is a UGC1 gallery. This is the milli-charged particle detector, or should we say feebly charged particle detector. It's 4 complete sections of 100 blocks of scintillator, 75 centimeters long, read out, each section read out by a PMT. And the idea is that a fractionally charged particle would traverse this array and actually travel along 3 meters of scintillator. Thus, even a small charge will give a reasonable signal, and this is the basic unit. Of course, it's surrounded by a hermetic veto layer, and the coincidence of these 4 PMTs essentially rules out any backgrounds from dark currents or whatever in the detector, in the PMTs, or any intrinsic radiation-induced signals in the bars. The calibration is carried out by blue LEDs on each of the bars and throughout the detector, and a neutral density filter that helps us make a lepton, like a muon, that goes through quite normally from the intersection point, make it look like a milli-charged particle so that we can do an absolute calibration. We've recently decided to put what we call the outrigger. This is the front of the detector I just showed you, 1 meter by 1 meter, 100 bars in each section. And then these outriggers on each side, which are 5 centimeters thick and angled to give a slightly bigger passage through the scintillator, like 7 centimeters, we'll be able to look for, should we say, fractionally charged particles with a higher charge, so we won't be as sensitive as this central piece here, but because of the area here, we'll be able to make to do a lot better in the medium fractional charge area. And these detectors are currently under construction, and we're actually getting the technical proposals through now. So what can we expect to do with this milli-charged particle? If we look at a couple of diagrams on the left, we have limits that can be placed at run 3, where we have the decay of a dark photon to fractionally charged particle pairs, and we can see the limits here. We have the fractional charge down to 10 to the minus 3 and thousandths of the electric charge. And here we have the mass of the milli-charged particle. And this is what we can do with these, the limits we can place with these various luminosities. And in this case, we have a heavy neutrino production where the heavy neutrino has a large electric dipole moment, which is the thing that interacts electromagnetically. And here we see the limits where we have electric dipole moment of the new neutrino against the mass of the new neutrino. Sorry. So when we look at the long-lived particle detector, MAP1, we see where we will take as a physics process a BDK, an inclusive BDK to a light scalar that decays to 2 muons. It's a usual example that's used. And here we see the sort of coupling there, sine squared theta, against the mass of the neutral, the scalar, the light scalar, the new light scalar. And we can see the limits from MAP1 here with 300 inverse femtobarns. And we can see that compared to the limits that you expect from a Codex B, which is another detector that's going to be placed in the LHCb region specifically to search for long-lived particles. The bottom, we see the reach compared to Methuselah and SHIP as well. Here we see Methuselah, and here we see SHIP. And we can see that what the nice thing about MAP1 is it covers a region between LHCb, should we say a more conventional LHCb detector, and the new detectors like Methuselah. It covers this kind of a gulf between the two. So phase 3, we would extend the MAP1 detector along the UGC1 tunnel so that we go from 5 degrees to 25 degrees. And this, we'll use the same technology, which is essentially fine grain hodoscopes, scintillator hodoscopes, to avoid gas and so on and so forth, which tend to become expensive and have safety problems. And then we see if we look at MAP2, we extend our search reach here out here, and you can see that now we're fully competitive with SHIP for this channel anyway. And for Methuselah, we move into more space than Methuselah, and we cover, again, the space between LHCb and Methuselah, this gulf between the two. So we're pursuing a useful function of being complementary not only to the LHC detectors, but to the new proposed large long-lived particle detectors. This is where we have this is another example where we have the right-handed neutrinos from the decay of an additional neutral Z boson. Here's the paper, and you can see MAP2 filling again the space between LHCb and Methuselah. And here we see the other detectors that proposed Codex B and Phaser. Of course, Phaser 1 is now running, but this is Phaser 2. So we can see that, again, we do some useful work. So concluding remarks, I'd like to quote Marcel Proust. And he said, the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And we'd like to think that dedicated search experiments such as Metal Map are the new eyes of the LHC. Thank you.
Yeah, thank you very much. Very interesting talk. So any question, comment?
I have a question. So James, can you explain a little bit about why you don't have the problem of the non-perturbative magnetic coupling when you produce monopoles in heavy ion collisions?
Yeah, I'll just go back to that slide. It's not because it's a heavy ion collision, it's because the monopole pairs up, there we go. The monopole pairs are produced via the Schwinger mechanism. So it's not an interaction product, it's more, I would say, barrier penetration or tunneling process. And it doesn't, it's not a, it doesn't have the problem of this non-perturbative sequence that you use to calculate the cross-section.
Okay, and in terms of the mass range that you would be able to cover with this mechanism would be similar to that of the usual proto-proto collisions?
No, it's not as good as that. But the point is, because we have these benefits, for example, if the monopole produced by Drell-Yan were not point-like, then it's likely that the cross-section would be so exponentially suppressed you wouldn't see the monopole. This is not a problem with the Schwinger mechanism. So this could be the first time we ever have the chance of seeing a monopole, if you understand my meaning. Because if monopoles are not point-like.
Right. Okay. Thank you very much.
Okay, thank you. And other question from Todd?
Yeah, thanks, James. Could you go over why in the highly ionizing you have a greater reach to low beta compared to CMS and Atlas? I didn't quite catch that.
Okay, so I'll go to these. Is that what you mean here? You mean low beta? I'm not quite sure.
You said somewhere you can go down to 1 over beta of 10,
oh, so we can go to
beta of 1 over 10. Sorry.
Z upon beta of 5. Now, the reason that we don't have the background is because we're sensitive only to particles if Z upon beta is greater than 5. Let's say beta is 1, whose charge is greater than 5 then, right? So we know there are no standard model backgrounds that give you that. You can get it from, of course, heavy ion collisions, but heavy ion, we're looking in PP anyway, but heavy ions you don't get heavy ion fragments coming out of the beam pipes, essentially, the detector. So we don't have standard model backgrounds, and we go down to a Z upon beta of 5. Now, of course, the standard particle detectors are designed to search for particles with a charge of 1, and most of the time, the particle can be more highly ionizing than that, but we don't even start to see anything until Z upon beta is greater than 5. Do you understand? Explain that properly for you?
I guess I'm not seeing why that can't be done in Atlas and CMS. You need to think
because it is. For example, CMS hasn't published a result yet, so I'll show you the Atlas result. So they can look for charges of 1 and 2, as shown here, but the real problem is they're massive detectors. They're not really made to look for highly ionizing particles, and the highly ionizing particles lose an incredible amount of energy very quickly because they're highly ionizing and probably quite heavy, right? So they're more absorptive than the metal, which surrounds essentially an open intersection region. The LHCb intersection region is not like, as you know, not like the conventional CMS or Atlas detectors. You actually, we can get within a meter of the intersection point with no real material between us and the interaction point besides the vacuum vessel of the Velo detector.
Okay, so I mean, CMS has gone up to 8E previously, and Atlas has gone much higher than that.
Yeah, they can. I'm only showing monopoles here, right?
Well, and I was actually talking about you had a later result on HIPs.
Yeah, and they go up to 100, I believe. If you look at this is for dions, we've got a ECO result coming out, highly charged particle result. They go up to about, before they run out, they go up to about 100, I think, Atlas in their latest result. Yeah. And we've got a result coming out that shows we go to about 150, 160. Okay. The only reason for that is we're a lighter detector nearer to the interaction point, and we're doing things that we're designed to do. Here, okay. We can see we go up to about 180 or something.
All right, I see. Okay, thank you.
We're designed to do that.
Okay, thank you for nice talk. And I think we now close this session. And I thank you for all the speaker and audience. And see you in the afternoon.
Okay, bye-bye.